Think about the device you're watching this on right now. Your phone, your computer. Our entire modern world is powered by billions of tiny little engines. But what's the secret sauce? What's the one invention that makes it all possible? Well, it's not a gear or a motor. It's a special kind of material, a substance we learn to control with almost magical precision. And that is the humble semiconductor. Let's pull back the curtain and see how it works.
All right, so here's our game plan. We're going to unravel the whole story. First, we'll look at the clunky, old-school tech that semiconductors replaced. Then we'll dive right into the physics that makes them tick. After that, we'll see how scientists basically learned to hack these materials, use that hack to build the most fundamental electronic gate imaginable, and finally, see how that tiny little gate solves a massive problem for every single gadget you own. So to really get why this was such a game changer, we have to hop in a time machine. Because before our sleek, solid-state world, the dawn of electronics was lit by the glow of something very, very different, the vacuum tube. And honestly, the difference was just night and day. Vacuum tubes were these big, fragile glass bulbs. They got incredibly hot, they sucked up a ton of power, and they burned out all the time. If you wanted to build anything remotely complex, like an early computer, you needed entire rooms filled with them. The dream, the holy grail, was a solid-state solution. No moving parts, no heated filaments, no vacuum, just a solid little chunk of material that was small, efficient, and super reliable. The only question was, what on earth could actually do that job? Well, the answer wasn't some exotic, newly discovered element. Nope, it was hiding in plain sight, in a really unique class of materials that sit on this fascinating knife's edge between letting electricity flow freely and stopping it completely. So you can pretty much sort all materials into three basic camps. On one end, you've got your conductors, like copper and other metals. Electricity just zips right through. On the complete opposite end, you have insulators, like rubber or glass, which stop electricity cold. But right there in the middle, that's the Goldilocks zone. That's where semiconductors live. They aren't great conductors, and they aren't great insulators, and that mediocrity is precisely what makes them so incredibly powerful. To really see why, let's picture the electrons inside these materials as people living in an apartment building. Now, they can only exist on certain energy floors, or bands. Most of them hang out on the valence band. Think of it as a crowded ground floor, where they're all stuck in their apartments, basically bound to their atoms. For electricity to flow, an electron has to get enough of an energy boost to jump up to the conduction band. That's the empty party floor on top, where it's totally free to roam around the building. Now, in a metal, this is super easy. The ground floor and the party floor, the valence and conduction bands, they actually overlap. There's no staircase, no barrier, nothing. Electrons can just casually wander from one to the other with zero effort. That's why metals are such fantastic conductors. Okay, now let's look at an insulator. Here, the energy gap between the bands is massive. It's like the party floor is 20 stories up and the elevator's broken. It's practically impossible for an electron to get enough energy to make that huge leap. So, no electrons make it to the conduction band, and no electricity flows. Simple as that. And this is where semiconductors hit that perfect sweet spot. They have an energy gap, but it's small, it's manageable. Like the party floor is just one short flight of stairs away. A little bit of energy from, say, heat or light is all it takes for an electron to make the jump. And this is the key takeaway, the whole game right here. Their conductivity isn't fixed. We can change it. We can control it. But here's the twist. A totally pure semiconductor on its own is, well, it's still not that useful. Its conductivity is just too low. The real magic, the breakthrough, happens when scientists figured out how to intentionally corrupt it. They learned how to hack the material by adding very precise impurities. So let's take a look at a crystal of pure silicon. Every single silicon atom has 4 outer electrons, and it forms 4 really strong bonds with its neighbors, sharing those electrons. It's a perfect, stable, and very orderly structure. But that perfection is also a problem. It means all the electrons are locked tightly in place. There are hardly any free carriers to move around and conduct electricity.
This amazing hack is called doping, and what it means is we deliberately and very precisely sneak a tiny amount of an impurity into that perfect silicon crystal. I know, it sounds like we're ruining it, right? But this controlled contamination is the absolute key. It intentionally breaks the perfect balance of the crystal, and in doing so, it unlocks its incredible potential.
And we can do this in 2 different ways. On the left, we can add an element like arsenic, which has 5 outer electrons. 4 of them bond perfectly with the surrounding silicon, but that 5th electron is just left over. It's an extra, it's loosely attached, and it's super easy to set free, which gives us an excess of negative charge carriers. We call this N-type. Or, on the right, we can do the opposite. We can add an element like boron, which only has 3 outer electrons. It forms 3 bonds, but for that 4th bond, it's missing an electron. This creates a vacancy, a spot where an electron should be. Physicists call this a hole. A great way to think of it is like a bubble in a liquid. The bubble itself is nothing, but it moves around as if it's a real particle. And this hole acts just like a positive charge carrier. We call this p-type silicon. Okay, so now we've engineered 2 brand new types of silicon, one with extra electrons and one with extra holes. On their own, neither one is all that special. But when you bring them together, when you stick them side by side, something truly incredible happens. You create the most fundamental component in all of modern electronics. The instant these 2 materials touch, a little bit of chaos erupts right at the border. The free electrons on the N side see all those empty holes on the P side, and they just rush over to fill them in. But this movement creates a thin layer right at the junction that's now depleted of any free charges. And here's the crucial part. This process creates a built-in electric field, like a tiny internal battery, that forms a barrier and prevents any more charges from crossing over. This whole structure, this barrier, is the heart of what we call the PN junction. And this is where we get to take the wheel. By connecting an external battery, we can totally manipulate that barrier. If we connect the positive end of the battery to the P side, it pushes the charge carriers toward the junction, which shrinks the barrier and basically opens the floodgates for current to flow. That's what we call forward bias. But if we flip the battery around, we pull the carriers away from the junction. This makes the barrier even bigger, even stronger, and it stops the flow almost completely. And you guessed it, that's reverse bias. The result is what you're seeing right here. This device, which we now call a diode, acts just like a one-way street for electricity. This graph tells the whole story. If you apply a positive voltage, the forward direction, current flows super easily once you get past a tiny little threshold. But if you try to apply a negative voltage in reverse, the gate stays shut. Almost zero current gets through. We've built an electronic one-way turnstile. So a one-way gate for electricity. You might be thinking, okay, cool, but so what? Well, it turns out this ridiculously simple device solves one of the single biggest challenges for every single electronic gadget we use today. Here's the deal. The power that comes out of our wall sockets is alternating current, or AC. That means the voltage is constantly swinging back and forth, positive, then negative, 50 or 60 times every second. But all our delicate electronics, our phones, our laptops, all of it, they can't handle that. They need a smooth, stable, one-way flow of power. They need direct current, or DC. So how in the world do we convert that messy AC into clean DC? You already know the answer. We use our diode. Let's just pop one into the circuit. When the AC voltage is positive, our diode is forward biased, the gate is open, and current flows right on through. But then, when the AC voltage swings negative, the diode becomes reverse biased, the gate slams shut, and the current is completely blocked. And just like that, we've literally chopped off the entire negative half of the wave. What's left is a bumpy, pulsating current, but it's only going in one direction. This process is called rectification. But why waste half the power? We can do even better. A full-wave rectifier uses a really clever arrangement of diodes. Instead of just blocking the negative part of the wave, it actually flips it over and turns it into another positive pulse. So now we're using the full energy of the original AC signal, which gives us a much more consistent, though still pretty bumpy DC output. We're almost there, but we still have these bumps to deal with. To fix that, we add one last simple component, a capacitor. You can think of it like a tiny water tower or a super fast charging battery. It charges up to the max at the peak of each pulse, and then, as the voltage starts to drop, it releases that stored energy to fill in the valleys. And just like that, the bumpy, pulsating mess is transformed into the smooth, stable DC power that our entire digital world needs to live. So there you have it. We started with a strange material that was neither a good conductor nor a good insulator. We learned to hack it, to control it, and we built a one-way gate. And with that simple little gate, we solved the fundamental problem of how to power all of our modern electronics. This PN junction is the absolute bedrock of it all, but it's really only the first step. So it leaves you with a question, right?
If joining two layers of the stuff gives you a one-way gate, what kind of magic can you create when you add a third?